Hello students, welcome. Professor Henkle here. What are all those boats doing on the ground? Shouldn't boats be floating in the water? Yes, but every day the level of the ocean at coastlines rises and it falls, and these are called tides. Let's get into it. There's a lot to learn all about the ocean's tides. So please begin by watching this KQED special on watching the tides. It sets us up. So go ahead, pause, watch. Welcome back. I hope you like that. Very cool. What we're going to do today, let's do it. Tides, the periodic raising and lowering of the ocean sea level. Here we can see the Bay of Fundy, which has the greatest tidal range, about 60 feet roughly, with boats on the ground. Boats are pretty high. It's pretty incredible. So tides happen. Let's just lay it out there. Why do we have tides? The Earth, the Sun, and the Moon exert forces of gravity on each other, and that force of gravity is felt on Earth's oceans. We're going to get much more into this. This was identified by the Greek scientist Pytheas in 330 BCE, before the Common Era. Isaac Newton was able to identify and start to lay the groundwork for our modern understanding by developing the law of gravitation. So Isaac Newton's law of universal gravitation states that gravity is a factor of the mass of one object times the mass of the other object divided by the square of how far they are apart from each other, or the radius. There's also a gravitational constant in there. So basically it's what are the mass of two objects and how far away they are from each other is going to be the influence on the force of gravity on either one of those objects. Check out Professor Dave give us a little rundown on some physics. Awesome. Continuing on. So the Moon, the Sun, Earth are exerting an influence of gravity on each other. Now the Earth's gravity pulls the Moon into its orbit, so the Moon doesn't just fly off. The Moon's gravity pulls water towards it. The Sun's gravity keeps Earth in its orbit and also pulls Earth's water because Earth's water is liquid. Now, what that does is it creates bulges of Earth's water that the Earth then rotates in and out of twice a day because Earth spins on an axis. So here's the Moon. Force of gravity towards the Moon creates a bulge that the Earth rotates through. So the bulge always faces the Moon as Earth rotates through it, giving certain areas of Earth a high tide, while other areas have a low tide. So the tidal bulges are the reason that we have tides as Earth rotates in and out of the tidal bulge created by the force of gravity from the Sun, the Earth, and the Moon. So here's the lunar bulge. There's also a solar bulge. The Sun is much bigger than the Moon, but it is also much further. Here we can see Sun to Moon, Sun to Earth, Earth to Moon. The effect of Moon's gravity on the oceans is about twice that of the Sun, even though the Sun is much bigger because of the distance. Mass 1 times mass 2 divided by the distance, or the radius squared. So the bigger the distance, the smaller the influence of gravity. Okay, got it. So we've got the Sun creating a solar bulge, the Moon creating a lunar bulge. They're pulling Earth's water in certain directions. And there's a center of mass between the Earth and the Moon, known as the barycenter, right? It's kind of like the Moon is out here, the Earth is in here. The Earth is much bigger than the Moon. The mass is much greater. So their center of mass is actually located at some point within the Earth. This is why the moon doesn't just go flying out into outer space, because they share a common center of mass between them that is actually located inside of the Earth. Now, I don't know why this is an S, it should be an M. But the moon and Earth are going to exert forces of gravity. The force of gravity towards the moon, the tidal force, is balanced by the inertial force because of the barycenter and how they're moving around each other. The inertial force and the gravitational force are equal and opposite, so the moon doesn't just go flying off into outer space. Moon is kept within Earth's orbit with the inertial force. There's a force of gravity towards the moon. That force of gravity actually pulls Earth's water to create the lunar bulge, similar to the solar bulge. So, okay, what the heck? The sun, the Earth, the moon. Just the Earth and the moon. The moon is circling around the Earth. There's a force of gravity from Earth to the moon. There's a shared balance point between them called the barycenter. Now, as the moon spins around the Earth, there's inertia in the opposite direction that keeps moon in its orbit. Same is true for the Earth and the sun. There's a force of gravity towards the sun. There's an inertial force in the opposite direction that keeps Earth in the sun's orbit. Now, with the force of gravity towards both the moon and the sun, Earth's water gets stretched out in the direction of them, causing tides to occur. Okay. So, we're talking a lot about the moon. The moon orbits around Earth once every 28 days. And along that pathway, there are different phases of the moon. New moon, full moon, quarter moon, waxing crescent, waxing gibbous, waning crescent. Here we can see along the 28-day cycle. We know it as full moon when we can see what appears like a full circle in the sky. We know it as new moon when we can't see. It's basically the orientation of the moon to the sun. Quarter moon and three-quarter moon, we see a quarter of the moon, and it's when the orientation is 90 degrees. This gives us spring tides and neap tides. Okay, follow me here. Here's the sun. Here's the Earth. New moon. We can't see any moon because the sun is illuminating the side we can't see. Full moon. The sun is illuminating the side that we can see. The moon and the sun are in line with each other, so the solar bulge and the lunar bulge complement. Here we have the highest high tides and the lowest low tides, the greatest tidal range. At quarter moon and three-quarter moon, the solar bulge and the lunar bulge are opposite each other. So the tidal range is going to be the smallest, the lowest high tides and the highest low tides. I know this is confusing. Stay with me. So depending on where the moon is relative to the sun, we have high tides, high tides, and low tides, or not so much. The difference between the highest high tide and the lowest low tide changes, giving us an idealized version. So here, if this is tide height over days, spring tides, when the sun and the moon and the earth are all in line, highest high tide, lowest low tide. Neap tides, when the sun and the earth are 90 degrees to the moon, lowest high tides, highest low tide, smallest tidal range, the difference between high and low tide. Highest tidal range, biggest tidal range, the difference between high tide and low tide. Now, this is what tides would look like in a perfect world, equilibrium tide theory. There's 2 high tides and 2 low tides occurring at the same time every day, producing similar heights all year long. This does not occur anywhere ever. It's ideal. What do we have? We have continents, we have coastlines, we have 400 other factors that are going to create their own individual little influences on what we see in the tides. That's a lot of data to account for. So real tides have continents with friction and a seafloor that modifies the tidal bulges. Tides are forced waves that are not freely propagating. The idealized tidal bulges cannot keep up, and the lunar tides cannot keep up with Earth's rotation. So here we see actual tidal data, Monterey's tide chart for March. High tide, low tide, high, oh, low, high, low, high, a little bit of low. So this is a mixed tidal schedule. It's repetitive, but it changes. And the time of the low tide changes every single day. Why is that? Well, that is because the tidal day is longer than the solar day by about 50 minutes. The time it takes for Earth to do one full rotation is 24 hours. There's 24 hours in a day, right? 24 hours in a day? Yes. But as Earth is rotating, the moon is also orbiting. So to get back to the place where the moon is in the same location takes an additional 50 minutes. The lunar calendar and the solar calendar are not the same. The lunar day and the solar day are not the same, giving us a different time for the high tide and the low tide successively every day, offset by about 50 minutes. Now, you bring that in, you bring in the angular distance of the moon or the sun above or below Earth's equator, which changes. Sun to Earth, it's 23.5 degrees. Moon to Earth, it's 28.5 degrees. So the lunar and the solar bulges shift from the equator up to 28.5 degrees, up to 23.5 degrees, causing unequal tides. So more factors, more variables. It's more complex than, oh, the gravity stretches out the moon, or the gravity of the moon stretches out the oceans, and we rotate in and out twice a day. Nope. Actually, Earth is here orbiting the sun. The moon orbits Earth. The lunar day longer than the solar day. The influence of the moon twice that of the influence of the sun. When the Earth, the moon, and the sun line up, they all work together. And when the sun, the Earth, and the moon are at 90 degrees, they cancel each other out. This is so cool. I love it. Let's bring in more. There's also continents. So continents are going to influence tides. Tides are going to have what's called amphidromic circulation. The amphidromic point is basically where there's no tidal range. And so tides are going to rotate circularly outwards from these areas, creating a global distribution of unequal tides. Because I know this is what the heck is going on here. Further making the situation more complex, because there's continents and tides interact with continents, there's area where there's no tidal range, and then spiraling out from those areas in a circular way, tidal ranges are shifted. Now, we understand these because we can predict tides. We can predict what the tides are going to be, how they're going to be. When you input all of these information in the computer models, the output is, here's our expected tidal range, which can be affected by all these different variables, including different storms at sea for different waves. So I've mentioned this before, the tidal range. It's the difference between high and low tide. It varies greatly all over the world. In some areas, like the Mediterranean Sea, it can be only 10 centimeters. Other areas, like the Bay of Fundy, up to 56 feet. So check out this video. It's so cool. You're going to love it. Now, as scientists, as humans who want to understand, organize, classify, compartmentalize, put things in a box. How do we do it with tides? So 3 specific: diurnal, semi-diurnal, mixed. Diurnal consists of 1 high tide, 1 low tide. Common in the Gulf of Mexico, west coast of Alaska, some parts of Southeast Asia. Semi-diurnal, 2 low, 2 high, equal to each other, found in North America, Australia, west coast of Africa, and some of Europe. Mixed semi-diurnal, so 2 low, 2 high. The high tides are of different values. The low tides are of different values. This is what we experience here along the Pacific coast of North America and all over the world. So here we see that mixed are the most common. North America, South America, through some of Southern Asia, the Indonesian islands, parts of Australia. But then you've got lots of semi-diurnal. Diurnal is going to be the least common of all of them. Global distribution of tides, because wherever there are coastlines, the intersection of the oceans and land, waves are going to arrive, and the effect of tidal influence is going to occur. So when we're looking at these coastal areas, intersections, we've got flood currents that are water rushing up towards the shore. Ebb currents, the ebb and flow, I guess you could call it the ebb and flood, right, of the tides towards land or away from land. Flood currents go up rivers or bays. Ebb currents go away from rivers or bays. And there's a peak and a trough where there's no movement of the high tide within the current motion, right? And so at some point, we've got low slack water where we're going from ebb current to flood current, high slack water where we're going from flood current to ebb current, back and forth. Here we can see the water goes out, ebb, the water comes in, flood, the water goes out, ebb. High slack water is the difference between where these points are, giving us a couple cool features for tides. Standing waves, which is a wave that is self-perpetuating because of the movement. Here you can see surfers on the side, these big waves. There's a surfer that's inside of it. And also tidal bores. So this is a big wave that's making its way up a river where you have an abrupt flood tide and a short ebb tide phase, a low-lying river with a seaward current. These are, wherever there's waves, there's surfers. Surfers love waves. Wherever there's beauty on Earth's playground, there are humans who are out having fun, experiencing that beauty, and playing on some of Earth's natural features. So standing waves, tidal bores, these are some of the gifts of nature for us to go out, to enjoy, and to experience. Tidal bore surfing. Check it out. So tides are a really important component of coastlines. Tides are the results of the Earth, the moon, and the sun interacting together. When these 3 interact, they have a tidal range. And if there was nothing on Earth, they'd have this predictable, idealized pattern. But there's continents, there's ocean, there's crust, as well as water. So tides do not behave in an idealized manner. In fact, they are very dynamic and influenced by continents, friction, and over 400 other variables. Tides actually can be used to prove that the sun is the center of the solar system, not the Earth. So it's amazing when we can observe natural features and we can understand our place in the universe because of it. Thank you so much. I appreciate your attention. I hope you learned a lot about our tides and you enjoyed the content of today's lecture. Thank you so much.